On April 9, 1940, Nazi Germany launched its invasion of Denmark and Norway. The following day, April 10th, a telephone rang inside a modest office building in Inglewood, California. On the line was a British liaison officer from the Purchasing Commission, his voice strained with urgency. Europe was preparing for something even worse. Within a month, Hitler would push west into France and the Low Countries. The Royal Air Force was already losing aircraft faster than its factories could replace them. Britain needed fighter planes immediately. Not in 2 years, not in 1 year, right now. The message was delivered to James Dutch Kindleberger, the president of North American Aviation. He listened to the specifications: long range, high speed, heavy armament, combat ready. Then the British officer added one final requirement. The first prototype must be delivered in 120 days. Kindleberger almost dropped the receiver. Designing a fighter aircraft from the ground up in 120 days was beyond unreasonable. Most fighters required 2 to 3 years of development. The P-40 Warhawk had taken 30 months, and the P-38 Lightning nearly 4 years. 120 days wasn't ambitious, it was impossible. Kindleberger called an emergency meeting. His engineering team filed into the conference room. He outlined what the British were asking for, then posed a blunt question that hung in the air like smoke. Can we do this? The room instantly erupted. Experienced engineers shook their heads. It couldn't be done. The idea was absurd. Wind tunnel testing alone required 6 months, and stress analysis took several more. A fighter plane couldn't simply be willed into existence. Physics didn't bend to deadlines. But at the back of the room, a quiet man with a German accent raised his hand. His name was Edgar Schmued, and he said 3 words that would alter the course of World War II. I can do it. This is the story of how one engineer accepted an impossible challenge, how he designed a fighter in 117 days, and how that aircraft became the deadliest American fighter of the war. The engineers who insisted it couldn't be done were correct on one point. It was impossible. But no one ever told Edgar Schmued that. To understand how Schmued managed the impossible, it helps to know what he had been doing long before that urgent British phone call. Edgar Schmued was born in Hornbach, Germany, a small town in the Palatinate. He grew up during the First World War, watching primitive biplanes battle above the Western Front. By the age of 16, he was sketching aircraft designs in the margins of his school notebooks. By 21, he had become a skilled mechanical engineer, largely self-taught after apprenticeships in engine shops and manufacturing plants across Germany. He went on to work for Daimler, then Fokker in the Netherlands, designing commercial aircraft. In 1925, he emigrated first to Brazil and later to the United States. By the mid-1930s, he had become an American citizen and joined North American Aviation in early 1936 as a preliminary design engineer, later advancing to chief of preliminary design. But Schmued possessed something that set him apart from every other aircraft engineer in the country. He believed war was inevitable, and he believed the United States was dangerously unprepared. In 1936, while his co-workers were developing basic trainers for the Army Air Corps, Schmued began a personal side project. During evenings, weekends, and lunch breaks, he started sketching fighter concepts, not because anyone had asked him to, not because the company required one, but because he was convinced that when war arrived, America would need the finest fighter aircraft in the world. For 4 years, he filled notebook after notebook with calculations. He studied every fighter type then flying: the British Spitfire, the German Messerschmitt Bf-109, the Japanese Zero. He examined their strengths, dissected their weaknesses, and set out to design something superior. He produced wing profiles that reduced drag, fuselage layouts that minimized weight, cooling systems engineered to offset their own aerodynamic penalties. He calculated performance goals that no American aircraft had ever achieved, ranges that sounded like fantasy. His colleagues thought he was wasting his time. America wasn't at war. No one was buying fighters. But Schmued kept sketching, refining, improving. So when that British call came in April 1940, and when Kindleberger asked whether anyone could design a fighter in 120 days, Schmued did not hesitate. He wasn't starting from nothing. He had already accumulated years of preliminary work, wing concepts, structural ideas, performance estimates that gave him a massive advantage over every other engineer in the room. All that remained was turning those ideas into a real aircraft. The British specifications were brutal. The fighter had to exceed 400 miles per hour, faster than anything in the American arsenal. At the same time, it had to be light enough to maneuver, strong enough for combat, and simple enough for mass production. Every aircraft designer understands the iron law. Speed demands power. Power requires large engines. Large engines add weight, and weight kills speed. It is a vicious cycle. For decades, engineers tried to solve it the same way: add horsepower, build bigger engines, and accept the weight penalty. Schmued approached the problem differently. What if the solution wasn't more power? What if the solution was less drag? He opened his notebooks. Inside were sketches of a revolutionary wing he had been refining, something based on a new idea known as laminar-flow airfoil. Drawing on research from NACA, the National Advisory Committee for Aeronautics, Schmued adapted their new 6 Series airfoils for a fighter wing. Traditional wings cause the airflow over their surfaces to become turbulent, producing drag that robbed an aircraft of speed. But this new wing had a radically different profile: thinner, smoother, with its thickest point positioned farther aft.
The theory behind the new wing profile suggested that air would move across its surface in smooth, layered sheets, laminar plates sliding past one another like stacked pieces of paper. With the airflow staying orderly instead of breaking into turbulence, drag would drop dramatically. But there was a major obstacle. No one had successfully built a laminar flow wing that actually worked under real combat conditions. The science was sound, yet achieving the required manufacturing precision was another matter entirely. If even a single rivet sat slightly out of alignment, if the surface had the smallest flaw or distortion, the laminar flow would collapse into turbulence. The result would be a wing that performed worse than a traditional design. It was risky, experimental. Many engineers dismissed the idea as unrealistic. Schmued didn't care. He had spent years refining the math. He was confident the concept would work, even if the aircraft achieved only partial laminar flow in real operations. He handed the wing drawings to his engineering team. They studied the blueprints, complex curves, exacting measurements, tolerances measured in thousandths of an inch. One of them finally asked, "Can we even manufacture this?" Schmued didn't hesitate. "We have to." Within 2 weeks, North American's factory was already forming the first wing panels. Sheet metal workers bent aluminum to tolerances they had never attempted before. Inspectors used micrometers to measure every surface. If any defect was found, the entire panel was scrapped and rebuilt from scratch. It was slow, costly, and infuriating. But once the first completed wing was mounted onto a test frame and airflow tests were run, the results spoke for themselves. Drag had been reduced dramatically, enough to measurably improve top speed and range. In real service, the wing would never maintain perfect laminar flow. Battle damage, rivets, exhaust stains, dirt, and gun ports would all disrupt it. But even partial laminar flow gave the Mustang a decisive advantage over every other fighter in the sky. Schmued had just solved the first impossible problem, speed. But speed was only half of the equation. The British also needed range. Their frontline fighters, Spitfires and Hurricanes, could stay airborne for about 90 minutes before fuel exhaustion. That was acceptable for defending the British Isles, but completely inadequate for escorting bombers deep into occupied Europe. The Americans faced the same limitation. The P-40 Warhawk could travel roughly 700 miles. The P-47 Thunderbolt, still in development, would manage maybe 500. Neither aircraft could accompany bombers on long raids into Germany. Escort fighters needed to fly side by side with bomber formations, protecting them all the way to the target and all the way home. The obvious answer was to add more fuel, but fuel weighs 6 pounds per gallon. More fuel created more weight. More weight demanded a larger engine. A larger engine added even more weight, and the entire cycle repeated. Schmued approached the problem from every possible direction. First, strip out unnecessary weight everywhere else. He designed the fuselage using semi-monocoque construction, where the aluminum skin itself carried structural loads reinforced only by a light internal frame. The idea is similar to a soda can. Its strength comes from the shell, not from any heavy framework inside. Every panel, rib, and structural member was optimized for the best strength-to-weight ratio. Second, maximize aerodynamic efficiency. The laminar-flow wing not only reduced drag, it also lowered fuel consumption. With less resistance, the engine didn't need to work as hard, which meant less fuel burned per mile. Third, redesign the cooling system. Schmued added a belly-mounted radiator scoop shaped to exploit the Meredith-effect. As air passed through the radiator, it heated, expanded, and accelerated as it exited the duct, creating a small jet-like thrust that offset the drag of cooling and sometimes even produced a slight net gain. Fourth, engineer the most efficient fuel layout possible. Schmued placed internal tanks in every feasible space, behind the cockpit, inside the wings, beneath the fuselage. He calculated fuel load and burn patterns so the aircraft would stay balanced as fuel was consumed. And he included fittings for external drop tanks, lightweight disposable tanks that could be jettisoned once empty. His team ran thousands of calculations: fuel consumption at various altitudes, power settings, speeds, and temperatures. They recalculated, verified, and recalculated again. The final numbers were extraordinary. With internal fuel alone, the aircraft could fly more than 900 miles. With drop tanks, its range exceeded 1,600 miles. 1,600 miles meant a fighter could take off from Britain, escort bombers all the way to Berlin, and return home. No other fighter on Earth could do that. Engineers from competing companies saw the numbers and declared them absurd, pure fantasy. But Schmued had the calculations and he trusted them. He had solved impossible problem number 2. But solving theoretical problems was one thing. Building a complete, functional aircraft in 120 days was something else entirely. Schmued assembled a team of 25 designers and draftsmen. He split them into groups: fuselage, wings, tail assembly, engine installation, landing gear. They worked in rotating shifts, 18 hours a day, 7 days a week. There were no computers, no CAD programs, no automated tools, only pencils, drafting tables, and slide rules. Every drawing was done by hand. Every measurement had to be manually calculated. Every stress load was derived using pages of equations. A single misplaced decimal point, a single miscalculated load factor, could later cost a pilot his life. Schmued moved among the groups like a battlefield commander directing his units. He reviewed every drawing, questioned assumptions, pushed for cleaner aerodynamics, simpler mechanics, lighter structures. When someone hit a design roadblock, he didn't send them off to deliberate. He stood beside them and solved it immediately, sketching ideas, running calculations in his head, making decisions in minutes that ordinarily required days of meetings. Meanwhile, the factory worked in lockstep with the design office. As soon as drawings were completed, they were rushed to the shop floor. Machinists began fabricating parts even as other sections of the aircraft were still being designed. It was organized chaos. A single design error could turn thousands of parts into scrap. But Schmued had already spent years working through the fundamentals. He knew which concepts were sound, he knew which weren't, and he trusted the mathematics behind his design choices. Each passing day meant one fewer day remaining to finish the prototype. Engineers collapsed at their drafting tables. Some slept on cots in the office. Others went days without returning home. Schmued was everywhere, inspecting welds, reviewing components, making last-second adjustments. He slept 4 hours a night on a cot in his office. Co-workers later said they never saw him eat a proper meal during those 4 months, only coffee and sandwiches while he reviewed drawings. May came and went. Then June, July, and August, and slowly, against all logic, the aircraft began to materialize. The wings were joined to the fuselage, the landing gear installed, the engine mounted, the fuel system fitted, the control surfaces connected. Then, on September 9, 1940, 117 days after the British request, 3 days ahead of schedule, the prototype rolled out of the factory. It sat on the Inglewood airfield under the California sun, bare aluminum shining like polished metal. Test pilot Vance Breeze walked around the aircraft, running his hand along the fuselage. Its lines were unlike anything he had ever seen, sleek, aggressive, elegant. On October 26, 1940, Breeze climbed into the cockpit for its maiden flight. The ground crew started the Allison V-1710 engine. It came alive with a roar, 1,200 horsepower shaking the entire airframe. Breeze taxied to the runway and advanced the throttle. The prototype accelerated smoothly, and at about 85 miles per hour, it lifted off the ground. Over the next weeks of testing, the performance numbers kept improving. The Mustang reached 382 miles per hour at 13,000 feet, one of the fastest American single-engine fighters tested up to that time, and created in less than 4 months. Edgar Schmued stood on the tarmac watching his creation slice through the sky. For years, it had existed only in the pages of his notebooks and in his imagination. Now it was real. The British named it the Mustang, and an impossible had become a reality.
The Mustang officially entered Royal Air Force service in early 1942, and British pilots immediately took to it. Below 15,000 feet, it was arguably the finest fighter in the sky, faster than the Spitfire, more agile than the Hurricane, and able to fly twice as far as either. But there was a serious issue. A critical flaw threatened to make the Mustang obsolete before it ever reached its potential. The Allison engine, excellent at low altitudes, rapidly lost power above 15,000 feet, and the air war over Europe was being fought high, 20,000, 25,000, even 30,000 feet, where the air was thin, frigid, and American bombers were fighting for their lives against Luftwaffe interceptors. At these heights, where lack of oxygen crippled engine performance, the Mustang was merely decent, not exceptional, not capable of escorting bombers deep into Germany, and not competitive against the best German fighters. The issue came down to basic physics. The Allison engine lacked the high-altitude supercharging necessary to maintain performance in thin air. As atmospheric pressure dropped, the engine struggled, lost horsepower, and became sluggish. Schmued had known this would be a vulnerability, but in April 1940, he had no alternative. The Allison was immediately available, proven reliable, and Britain needed fighters immediately, not years later after a new engine could be developed. So the Mustang carried out low-altitude missions over France, ground attack, reconnaissance, close support. It excelled in these roles, but it could not perform the mission that mattered most, acting as a long-range escort for bombers heading into the heart of Germany. Meanwhile, over the Reich, American bomber crews were dying in staggering numbers. The 8th Air Force was sending massive daylight formations, hundreds of B-17 flying fortresses loaded with explosives. Without long-range escorts, they were torn apart. American fighters such as the P-47 Thunderbolt could accompany them only part way. As soon as the escorts turned back at the German border, the Luftwaffe struck. Some raids lost 10% of their bombers. Entire groups vanished in a single afternoon. Something had to change. On April 30, 1942, Rolls-Royce test pilot Ronald Harker flew a Mustang at an RAF airfield. He landed thoroughly impressed, but frustrated. The airframe was outstanding. The engine was the weak link.
After the flight, Harker wrote a memo to his superiors containing a single bold proposal: install a Rolls-Royce Merlin. The Merlin engine powered the Spitfire. It was a two-stage supercharged marvel designed specifically for high-altitude combat. Its engine-driven compressor forced dense air into the intake, allowing it to produce full power even at extreme altitudes. At 30,000 feet, where the Allison suffocated, the Merlin produced well over 1,400 horsepower. It was heavier than the Allison, more complicated, more expensive, but it was precisely what the Mustang required. The proposal reached Schmued in California. He immediately reviewed his original calculations. The Mustang's structure had been built with enough margin for future upgrades. The engine mounts could be reworked, the cooling system redesigned. Everything was feasible. Schmued and his team returned to the drafting room. They rebuilt the entire engine installation: a larger radiator scoop, redesigned ducting and exit geometry, strengthened mounts, a revised center of gravity, and a modified fuel system. In Britain, engineers created an experimental version called the Mustang X, which first took to the air on October 13, 1942. In the United States, North American's XP-51B, equipped with a Packard-built Merlin, flew for the first time on November 30, 1942. When test pilot Bob Chilton climbed to 30,000 feet, the transformation was immediate. Where the Allison had gasped, the Merlin surged. Chilton pushed the throttle forward, 440 miles per hour at 30,000 feet. Over the radio, he could barely contain his excitement. It felt like an entirely different aircraft. The improvement was total. The Mustang hadn't merely been upgraded, it had been perfected. Equipped with the Merlin engine and external drop tanks, the P-51 Mustang could now exceed 1,600 miles of maximum range. More importantly, its combat radius, the distance it could fly to the fight effectively and return home, now covered the full trip from England to Berlin and back with fuel to spare. At altitude, it could outrun, outclimb, and outmaneuver any German fighter. Schmued had taken an impossible deadline and created an aircraft that rewrote the rules of air combat. By the spring of 1944, P-51 Mustangs were rolling out of factories in California and Texas by the hundreds. Entire U.S. 8th Air Force fighter groups in England converted to the Mustang, and the air war over Europe shifted instantly. For the first time, American bombers had escort fighters that could stay with them all the way, to the target deep inside Germany and all the way back with fuel to spare. Mustang pilots no longer had to turn home early. They had the range to fight, then fight again. Luftwaffe veterans, pilots hardened by years of brutal combat on multiple fronts, suddenly found themselves the hunted. American Mustangs appeared over Berlin, Munich, Vienna, skies the Germans once considered completely secure. The statistics were devastating. In the first half of 1944 alone, P-51s claimed roughly 1,500 Luftwaffe aircraft shot down. By the end of the war, U.S. Mustang groups claimed roughly 4,950 enemy aircraft destroyed in air-to-air combat, plus another 4,131 destroyed on the ground, more than any other Allied fighter in the European theater. And despite flying the most dangerous deep-penetration escort missions of the war, the Mustang maintained an exceptionally favorable loss rate. But the Mustang wasn't only an escort. It was used aggressively as a hunter-killer, ordered to strafe anything that moved: rail lines, airfields, trains, convoys, parked aircraft. It destroyed nearly 4,000 aircraft on the ground alone, planes that never had the chance to take off. German pilots wrote in their diaries that they felt as if they were being hunted. Every time they climbed into a cockpit, they understood they might not return. German ace Oberlieutenant Heinz Knoke, who survived the war with 33 victories, described the dread of facing Mustangs in 1944. German aircraft production couldn't keep up with the losses. Skilled pilots were irreplaceable, killed, captured, or injured beyond recovery. Their replacements were teenagers with 30 hours of flight training thrown against American aces with hundreds of combat missions. Captain Chuck Yeager, who would go on to break the sound barrier, flew Mustangs in 1944. He later recalled that by mid-1944, American pilots effectively controlled the sky. Whenever the Luftwaffe launched, they were gambling with their lives. Most lost the bet. On D-Day, June 6, 1944, the Luftwaffe managed only a few hundred sorties over Normandy. The Allies flew around 14,000. Estimates vary, but the reason does not. The Luftwaffe had been broken, and the P-51 Mustang was one of the primary reasons. By raw numbers, the Mustang was the deadliest fighter the United States fielded in World War II. Roughly 4,950 aerial victories, more than 4,100 destroyed on the ground, around 230 V-1 flying bombs intercepted, 15,000 aircraft built, and combat service in every theater from Europe to the Pacific. But the Mustang's true legacy is simpler than statistics. Before the Mustang, American bombers couldn't reach Germany's industrial core and survive. After the Mustang, they could.
Before the Mustang arrived, the Luftwaffe ruled the skies over Germany. After the Mustang entered combat, that dominance vanished. The aircraft that had been designed in an unbelievable 117 days seized air superiority from Nazi Germany, and without control of their own airspace, Germany had no path to victory. Yet there is one more detail about Edgar Schmued that makes this story feel almost Shakespearean in its irony. Edgar Schmued had been born in Germany, trained by German engineers, and educated in German factories, some of the same factories that later produced the designers who built the Luftwaffe's fighters. The aircraft that eventually shot down more Luftwaffe planes than any other was created by a man who grew up in the Palatinate region and learned his craft in Bavaria. German-built Luftwaffe icons, Messerschmitt Bf-109s designed by Willy Messerschmitt, Focke-Wulf 190s created by Kurt Tank, were destroyed in huge numbers by a fighter conceived by someone shaped by the very country they defended. In 1969, a journalist asked Schmued how he felt, as someone German by birth, about designing the fighter that devastated the Luftwaffe. Schmued's response was calm, deliberate, and final. "I am not a German. I left Germany in 1925. I became an American citizen in the mid-1930s. What I built for America, for freedom." He never courted fame. He never published memoirs, never sought the spotlight. While fighter aces became household names, Schmued remained almost invisible, an engineer, not a warrior. After the war, he continued working in aviation, contributing to designs such as the F-86 Sabre and several other aircraft, yet he still avoided celebrity. Mustang pilots who survived the war, men who entrusted their lives to the aircraft, spoke of it with deep reverence. Colonel Bud Anderson, who flew 116 combat missions and scored 16 victories in the Mustang, leaders said that the P-51 Mustang was the aircraft that brought its pilots home, a machine they trusted completely, crafted by an engineer who gave them a real chance to survive. Edgar Schmued passed away on June 1, 1985, at age 85 in Oceanside, California. His obituary in the New York Times was modest: no military funeral, no grand ceremonies, just a quiet burial. But every time a restored P-51 Mustang fires up at an air show, every time that Merlin engine unleashes its unmistakable growl, and every time that sleek laminar-flow wing slices through the air, Schmued's legacy rises again. Back in April 1940, when the British asked North American aviation for the impossible, most engineers said it couldn't be done. They said physics made it unachievable. They insisted no one could design a top-tier fighter aircraft in 120 days. They weren't wrong. By every conventional measure, it was impossible. But Schmued had been preparing for that impossible moment for years.
He had filled notebooks with calculations, drawn wings that existed only on paper, and worked out systems that no one had yet attempted. When the moment arrived, he was the only one ready for it. He solved 3 problems that seemed unsolvable: achieving speed without excessive weight, reaching extreme range without massive size, and meeting a deadline that defied reason. The result was the P-51 Mustang, the fastest, longest-range, most effective fighter of World War II, the aircraft that secured air superiority over Nazi Germany. Nearly 4,950 enemy aircraft destroyed in air combat, more than 4,100 destroyed on the ground, 15,000 built, decades of service. But the Mustang's true legacy isn't in the numbers. Its true meaning is the proof that impossible is merely an opinion, easily overturned by a single person with vision, expertise, and unbreakable resolve. Schmued demonstrated that genius doesn't require a committee, that innovation doesn't need years of bureaucracy, and that when the world demands the impossible, sometimes all it takes is someone who refuses to believe it can't be done. He designed America's deadliest fighter in 117 days, and in doing so, he helped win the war. The engineers who said it was impossible were right in theory. Edgar simply did it anyway.